Hello guys, welcome back, chapter 4, 5, day 3. You are going to need your calculator today, so get out that graphing calculator. And to get started, what we're going to be doing today is looking at stem plots, and we're going to be doing some numerical analysis, looking at mean, um, a little further discussion on mean, and getting into the standard deviation, something that was introduced to you back in algebra. And I'm going to show you where that standard deviation calculation actually comes from and really what it represents in the grand scheme of things. So Zach, my son, is interested in finding out how many text messages he is sending per day. Now, Zach is in second grade. No, he does not have a cell phone. So no, he is not sending text messages per day, but just go with the flow here. Some days he feels as though he's sending out many texts, while other days he feels as though he is only sending out a couple. He pulls up his Verizon detailed account from the last 3 months and randomly selects 20 days. For each of these days selected, he records how many texts he sent on that day. The data is given in the table below. So, what I would like to do is, if you have to pause the video to do this, take a moment and put those 20 pieces of data into list 1 of your calculator. So pause the video and do that now, please. All right, so now that you have that data in your calculator, in order to create a stem plot, what we really want to do is we want to put that data in order. And so right now, your data is probably not in any kind of order. All right, so the first data value, and depending on how you put it in, mine's 50, I did each column. So what we want to do is we want to put this data in order so it's easier to work with. So what we can do is if you go to list, which is second stat, and we go over to operations, OPS, we can sort our list in either ascending order or descending order. So if I choose number 1, ascending order, and I tell it, hey, calculator, can you sort list 1? So hit second, number 1, and hit enter. Now you don't see anything, but now if you go back into stat edit, you can see that your data is in order. Okay, now why is this useful? Well, let me show you why it's useful. Let me do this on my actual calculator in front of me for a second. Stat edit. Okay, so second list, operations, sort, list 1, stat edit. All right, so now it's on my calculator that's in front of me. So here's what we do. Scrolling down that list 1 in your calculator, we can see that the smallest value is 13, and it goes all the way up to 81. So the stems are going to represent the tens units here. So we start at 13, so we got 1, 2, 3, 4, 5, 6, 7, 8. And those are going to be the stems. And so what we have here, this is why putting everything in order is a lot easier to work with. We can see we have 13, 13, 13. So we put a 3 here, another 3, and another 3. Then we have 15 and 19. 15 and 19. All right, so now, kind of like a dot plot, we want to keep our spacing relatively even from one column to the next. So we've used this value, we've used this value, we've used that 19, that 13, and that 15. All right, so now we got 22, 23, 23. So 22, 23, 23, keeping everything lined up. 24, 26, 26. 24, 26, and 26. So we used the two 26s, two 23s, a 22, and a 24. So now we go to the 30s. What do we have for 30? We have 30, 31, 34, and 38. So 0, 1, 4, 8. 0, 1, 4, 8. Then we go to 40s and we have 49. We go to 50 and we have 50, 50, and 51. 50, 50, 51. And then we jump all the way down here to 81. Now, you look at that and you say, well, Mr. Johnson, we're missing something here. You're right, we are missing something. There's no context to this. We need some kind of context. So in this case, what we created, we create a key. And so what I do is, and you can do it either on the left here, over here, over here, it doesn't really matter where you put it, but 1 line 3 represents 13 text messages. And that's kind of the context part of a stem plot. All right. And literally, if you take your paper and you turn it 90 degrees counterclockwise, you basically have something that looks like a dot plot. Or if you were to put rectangles around each of those stacks, it looks like a histogram. All right. So it's kind of a combination of those two again. So down here is another example of stem plots on the left. And what we have are back-to-back stem plots on the right. And these ones you're going to see kind of coming up next week. We use these when we want to compare two distributions of data. All right. So let's say, like, for example, you had data from males and females and you wanted to compare them. Or let's say you had data from like Penfield High School and Fairport High School and you wanted to compare those sets of data. Or let's say you had data from, I don't know, iPhone phones and Google phones, or you want to compare Honda vehicles to Toyota vehicles. You have some kind of quantitative data for two different sets and you want to compare them to each other. So like everything else we talked about, there's pros and cons. So one of the pros is that we can see each individual data value, okay, like a dot plot, okay. So stem plots are very similar to dot plots, but instead of having dots, you have the numbers, okay. Another pro, you can see the shape, and specifically gaps. So if you look at our example, we have a kind of a big gap here all the way from the 51 to the 81. That's a pretty significant sized gap of 30 units there. If you look at this example here, we have a gap here. We have a little space. I would call that a space. We have a gap there. One of the pros can be used to compare distributions when I'm referring to the back-to-back stem plots that we have up above, because you never really see like a back-to-back dot plot. You don't see a back-to-back histogram, but we do have back-to-back stem plots, all right, which are a nice way to compare distributions. Another comparison we use, you're going to find out, is what we call parallel box plots, and that's where we put one box plot on top of the other on the same scale. But these are nice, and you see these in a variety of questions when we want to compare distributions. And a con, similar to the dot plot, is they are not ideal for large data sets. Okay? So in terms of quantitative data displays, that's the four that we're going to use. So you have the, let me back up for a second. We have the dot plot, we have the histogram, we have the box plot, and now you have the stem plot. So let's do some numerical analysis. What is the mean? Well, we know how to calculate the mean. You add up all your data values and you divide by however many data values there are. So in our situation, we have a sample of 2, 4, 6, 8, 10, 12, 14, 16. So we have 20 pieces of data. So we know that we're going to do the total sum divided by the number of data values, right? So in our case, we're going to do something divided by 20. So if you go to your calculator, because we're going to let the calculator do as much for us as we can, if you go to Stat, and you go to Calculate, and you choose one variable, Stats, and hit Enter, your data is in list 1. We don't have a frequency list, so we're going to leave that blank like we did the other day. Well, remember with the dice, we had a frequency list. We don't have that now. So we're just going to hit Calculate and hit Enter, and X bar is 31.55. So that means that our average is 31.55. Now, what was the sum of all of our text messages? Well, remember, the total sum divided by 20 gave us this answer. And so if I want to know what that total sum was, hint, 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 we're going to use this in just a second. The total sum is the average multiplied by however many data values there are. So if I go back to my calculator and do 31.55 times 20, second quit, 31.55 times 20, the total sum was 631 text messages. Okay? And we're going to use that in just a second. So 631 texts. Now, this version of mean is very easy, something you are familiar with. But this kind of question here is more of a high school stats kind of mean type of question. Let's imagine Zach took a larger sample of 30 days and had an average of 30.64 texts per day. And his big sister Brissa took a sample of 45 days and had an average of 24.89 texts per day. What would be the combined average for the number of texts per day for Brissa and Zach? So what we would want is we want the total number of texts over the total number of days. Now, Brissa had 45 days and Zach had 30 days. So we want to combine, we want to get a combined average. So we can't just add 24.89 and 30.64 and divide by 2 because these are not weighted the same. All right, so this is kind of like a weighted average. Fire drill, pause. All right, ladies and gentlemen, I am back. Just got back inside from a fire drill. Let me kind of think about where I was here. So we are trying to find the combined average for Zach and Brissa. I believe I was saying we can't just take these two numbers and add them up and divide by 2 because they're not an equal representation of days. So what do? Well, the total number of days that we're taking into account is 30 plus 45, which is 75 days. All right, what's the total number of texts? Well, here's what we know. We know that over 30 days, Zach had an average of 30.64. So how many texts did he send in total? Well, this goes back to what I just did up here. The total number of texts is his average multiplied by the number of days. So his average is 30.64 multiplied by 30. That's going to give us his total number of texts. So 30.64, hold up, let's do that in the calculator. 30.64 times 30. That's, I must have messed something up. Got a decimal value, but that's 919. And for Brissa, she had an average of 24.89 over 45 days. 24.89 times 45. That gives her 1,120. So now we have the total number of texts for Zach, the total number of texts for Brissa. And so 1120 plus 919 is 2,039 divided by 75. And now you have a combined average. Okay. So that kind of question is a little bit higher level in terms of going beyond your basic average that you're used to since like middle school. This whole idea of a combined average when you have two different sample sizes, a sample size of 30 and a sample size of 45. And you kind of have to work backwards to figure out your totals, so therefore you can get a new combined average. All right. Now, the other value I want to talk about here is the standard deviation. This is something that was first introduced back in algebra, and you kind of do it on your calculator, and you never really find out where it comes from. So the standard deviation measures the spread, the amount of variation, by looking at how far on average each observation is from the mean. All right, it is used to describe the spread or variation of a distribution. So In order to calculate standard deviation, we must first calculate something that's called variance. And variance is the quote-unquote average of the squared deviations. All right? So our average for our set of data, I believe, was 31.55. Did we figure that out yet? Or am I just, no, 31.55 right there. All right. So I'm going to take you through this step by step in your calculator to show you where the standard deviation comes from. All right. The average of the squared deviations. So, stat edit. Up in list 1, the first thing we're going to do is we're going to calculate the deviations. Basically, how far is each value from the mean? So we type in the rule, so make sure your cursor is up here in L2. We do L1 minus 31.55. Enter. So what that tells me is, that tells me how far each data value is from the mean. Now you say, well, Mr. Johnson, if it's the average deviation, why don't you just add up those values and divide by 20? Well, the thing is, if you were to add up all those values in L2, they're going to add up to be 0. And when you do 0 divided by 2, you're going to get 0, which would mean that there's no variation. Well, no, there is variation. So right now you have a bunch of negative deviations, and if you scroll down, then you have these positive deviations, and I promise you that if you add them all up, they're going to be 0. So what do we do next? We square them. Why do we square them? Because now it's going to make everything positive. So if we highlight L3, so get that cursor up there on L3, and do the rule L2 and square it, and hit enter, now everything is squared. Okay? So now that makes everything positive. So to find an average, we have to add all those values up. So now we want to add up everything that's in L3. So we're going to go to list, which is second stat. We're going to go over here to mathematics, and we're going to choose number 5, enter. It's just a sum. So, oh, nope, I don't want to be there. Sorry. Let's go back to our home screen. Home screen. Let's try that again. List, which is second stat, math, sum, enter. Everything in L3, which is 5678.95. 5678.95. So here's what we did. In L2, we did L1 minus 31.55, and then we did L2 squared. And we added up all those squared deviations to get 55,678.95. So to find the average, you would say, okay, I'm going to take this total sum and divide by 20. Well, we're not actually going to divide by 20. We're going to divide by n minus 1. So now we're going to take 5678.95, and you would think we would divide by 20. We're actually going to divide by 19. This is something that's going to come up multiple times, and I promise you I will explain later why we divide by 19 instead of 20. But we do 5678.95 divided by 19 is 298.89. And so that value is our variance value. And then what we got to do, the last step to get our standard deviation, is to take the square root. Well, why are we taking the square root? Because remember, back here, stat edit, to get from column 2 to column 3, we squared everything, so we got to kind of undo that process. So we take the square root of 298.89, second square root, second answer, and your standard deviation is about 17.28. And that's where standard deviation comes from. So in your calculator, when you do stat calculate one variable stats, enter, of everything in list 1, which is the original set of data, x bar is your mean, and S of x right there is the standard deviation for that sample of data 17.28, which represents, quote unquote, the average amount of deviation from the mean. And that's what standard deviation measures. The average, quote unquote, standard deviation from the mean. All right. So I will end on that. So go ahead and do the day 3 homework. And thank you very much.